I'd like to finish what we started talking about in class about using neural networks to classify short audio clips of digital synths. So the data set that we're going to start with is a bit like a professional version of what we did on homework 2 with FM synthesis and Carplus Strong and things like that. So this is called the Synth data set. It's from Google's Magenta group, which is a group that works on kind of artistic things. And so just to look at the data for a moment, get to know it. That's always an important thing to do. I'm going in here. I'm gonna look at some of the audio samples. So actually, and there's some metadata to go along with this. So if I wanted to, let's see about this clip right here. Organ electronic 057. Okay, let's see if we can find it. Organ electronic 057, and then 056 127. Okay, there's the clip. Let's listen to it. So there's the electronic organ. So each of these clips is 4 seconds long. Maybe we'll check one more out here. What about the guitar acoustic? 014 100. Okay. Guitar. Acoustic. And it was 014 100. Okay, there we go. Let's listen to it. What was it? Sounded a lot like Carplus Strong there. Just a little pluck. Okay, so if we look at the Synth data at the top level directory, we actually see 3 different folders. One of them is called the training set, the other one is called the validation set, and the last one is called the test set. So now that we're getting to real data, we need to be very careful about how we train this and how we test it. It's very important that we hold aside data that we don't look at during training, because otherwise we may just end up memorizing or overfitting to the training set. So we know the training set perfectly, but we have no ability to generalize our ability. So we're going to hold out some test set. There's also something called the validation set, which we won't get as much into here, but this is useful if you want to kind of change some of the parameters of the neural network. Some of these hyperparameters, not the direct parameters that you're using, but maybe things like how many neurons should be in this level, in this layer. So you can use a validation set to see how you're doing outside of the training set while you're varying those parameters, and then you have a test set that's different that you look at later. We're not going to worry about the validation set too much now, but I want to show you sort of how much data is in each of these. So in the training set, let's see. So if I were to say find Synth train and then word count. Okay, so there's about 289,000 clips. All right. So one of the things with neural nets is they're very data hungry. We need tons of examples for them to learn because they have a lot of parameters to tweak. So the more parameters you have, the more data you need. Okay, so that was a training set. What about the validation set? Okay, so a lot fewer for that, so 12,000, and then the test set. Okay, about 4,000. So actually, for the purposes of what I'm going to do, we're going to be making a pretty simple neural network comparatively, and we're actually doing a task that's simpler than what Magenta had in mind. Magenta was actually synthesizing, training a neural network to synthesize new clips. That is definitely harder than just looking at them and classifying them. So we're going to do something easier, so we don't need as much data. So what I'm actually going to do is use the validation set as the training set. So I don't need nearly as many examples. Okay, so for convenience for what we're about to do, and also to make it easier to distribute to you, I have put every single clip back to back in these 2 MP3 files, sampled at 8,000 samples per second, which is half the rate that Magenta gave us. Now doing that and then also compressing them in MP3 loses some audio fidelity. That's not what we would want to do if we were synthesizing things, but it's fine for our classification here. So let's just look in the test set real quick. So even the test set, which only has 4,000 examples, is about 4.5 hours of audio. So when I line all these 4-second clips back to back, there's quite a lot of examples. And I can just jump around and try to play different examples. And there's different instruments. Okay. But each one is 4 seconds. So that's our data. Now, if we want to load this in, we're going to recognize that each sample is a particular number of audio samples. So it's going to be the sample rate times the duration in seconds, which I'm also storing as an instance variable here called sample len. That's the duration in seconds. So this is the total number of audio samples that each little clip takes up. And the clips are back to back. So if I'm telling you to get the clip at a particular index, I need to jump past L times that index number of samples. So I need to jump past the first IDX clips. So I'd say just slice out the big audio of all of them back to back, starting at index L times IDX and going up to that index plus L. Okay. Also, in parallel, I've stored a text file which has the labels of each of these, which is some number starting at 0, which is going to index into this list of all the possible instruments. So, like, if the label was 2, that would be an acoustic brass, right? So 0, 1, 2. If the label was a 5, that would be an acoustic guitar. And so that's what the label means here. So I would say label equals self.labels at this index, IDX. But that turns out to be not exactly what we want to return as our output. So the input is going to be audio samples, possibly transformed somehow. But we don't want the output just to be this 0 indexed number, because we lose our interpretation of that as a probability, right? So now I'm going to output some number between like 0 and 19 or something. Whereas before, I was outputting a number between 0 and 1, and when that number was greater than 0.5, it meant a probability. So I want to do something a little bit more like that, where my network is going to estimate the probability of over all instruments, and I pick the one that has the highest probability, the maximum likelihood. So what we're going to do is not output that number directly, but instead output something called a one-hot vector. So just to show you an example, not on audio, but on a common data set called MNIST, where there's digits. So here there's 10 classes, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The network is supposed to learn how to output like what a digit is from an image of a digit. And so here we have 10 classes. And so if it's a 0, I could just output the 0, but I don't want to. Instead, I output a vector that has as many elements, so an array that has as many elements as there are classes. So in this case, there's 10 digits. And since it's a 0, the first one has, we're going to say, if we're doing perfectly, the first one has a probability of 1 of happening, and everything else has a probability of 0. If it's supposed to be outputting a 1, well then ideally the network will say that the element at index 1 has a perfect probability of happening, and the rest are 0, and so on and so forth. So that's called a one-hot vector. So it's as simple as putting a 1 at the index corresponding to the label that you have, and a 0 everywhere else. Now in practice, our network is going to output something a little bit in between. And so what we're going to do is have the network output to as many neurons as there are elements in our class. And then we're going to use something like the logistic function called softmax. It's actually a generalization of the logistic function to multi-class data. So given an array U of inputs, the softmax function is defined as the following vector valued function. So we have f of u at index I is equal to e raised to the u I the sum over all the other dimensions, actually including this, j equals 1 to n of e to the u j. Okay, let's make sure that came out right here. So one thing you notice here is that these are all going to sum to 1, because an individual one is then divided by the sum of everything. And so these can be interpreted as probabilities. To show you an example of this, here's softmax I put on a neural network that was trained to classify digits. So the neural network outputted 10 numbers, and then I ran softmax on them. So you see the neural network outputted this number. Definitely 1 is the biggest. Okay, now here, so 9 is the biggest, and so you see what happens is the softmax completely saturates on the one that wins. So it's part of the reason it's called softmax, because of the exponent. The one that is above the others is going to completely dominate in probability. So our neural network doesn't have to output like completely perfect numbers at the end, and it'll saturate here. And so this is what we're trying to get to match the ground truth that we have. And so the loss function between the softmax output and our ground truth one-hot vectors is actually also a generalization of something we've seen before. This is a generalization of the logistic loss. And so between an output y, a one-hot output y, and an estimate, it's the negative sum over all the dimensions of y and an xi times the log of the estimate of y. So this is a generalization of logistic loss. All right, so we figured out a way to turn these into probabilities. It looks kind of like the logistic function. Actually, over 2 classes, this is exactly going to be the logistic function. But now this is going to work with multiple classes. Okay, let's incorporate this whole one-hot thing into the output. So we know what we're looking for is an array that has as many elements as there are class labels. And so I'll go ahead and set up such an array. And the one element that should be non-zero should be 1. That will be an index label. And then I'll go ahead and move these from NumPy to torch as usual. Okay, so now we're ready to make a neural network to try to tell the different classes apart. So we could go ahead and start to try to make the first hidden layer. So I could say something like nn.linear, and so the number of inputs is going to be the number of audio samples, so that would be sample rate times the sample length. And let's say that the first hidden layer has 100 neurons, just to give it a lot of different options for trying to carve out interesting regions in the audio space. But this is going to be a bit of a problem because, well, this number is 32,000, and then times 100, that is going to be 3.2 million. So we'll need 3.2 million plus 100 bias parameters. So that's a lot of parameters, and maybe it'll work, but actually first I want to start off by going back and remembering that, okay, we can actually reduce the dimension of the raw audio. So if we go back to module 17, we're talking about the MEL spectrograms, MEL space spectrograms, and I showed that if you only choose 20 bins for a 1024 length window, you preserve all the information we need to kind of tell what the instrument is, even if we lose the notes. And that's what we're trying to do here. Actually, the notes, the individual pitches, are going to be a nuisance parameter. So we can use the MFCC here. So that's to remind you what we got away with only 20 numbers. So that was more than, what was it, almost I think a 50 times reduction in dimension, because we went from 1024 down to 20 dimensions. So that's a big savings. And so let's try to reduce the dimension, because then we won't have to learn nearly as many parameters. So what I'll do, instead of x, I'll actually use something called, I'll say x is equal to librosa.mfccx. I'll make sure I pass along. Oh, actually, it requires the parameters called y. And I'll say the sample rate is equal to, I'll make sure to specify that. And so that is going to do something like the MEL space spectrogram, which I'm showing here. It's going to just crunch on it a little bit more, turn it into something called the MEL frequency capture coefficients. But by default, Librosa also gives us 20 dimensions. And so what I'll do is this is actually going to be a two-dimensional array. So it's going to have 20 rows and however many columns. I'm just going to flatten it into a one-dimensional array. And so what that's doing is it's going to take each row and put them next to each other into a one-dimensional array. And so now if I look at, I guess I'll take an example of the data, and I'll look and see how long it is. You know, it used to be 32,000 samples, but if I look at, you know, the length of let's just say the first one in the train set. Well, actually, it looks like I just discovered a bug from before. I should have said, so the label somehow ended up as, that's interesting, the label somehow didn't end up as ints there. Okay, so I gotta fix that. Let's see if that fixes this bug here. And, oh, I think it was librosa.feature.mscc. Okay, we're almost there. So lots of little things. That's why you might notice the video jumping around a little bit, because it's easy to make mistakes. This stuff is very complicated code-wise. Okay, finally, I got it. All right. So if I look at, okay, what is the length of the data? So you see, okay, you see the data coming back, and then you see the one hot vector. So this is in class 0. So if I look at the data here, okay, 1260. So it used to be 32,000, but I've reduced the dimension to 1260. So that's a big reduction there. And so I'll be able to get away with many fewer parameters. Let me actually go ahead and store that number in a variable called dim here, and I'll use that number when I'm making my neural network. So I say, okay, the first layer here is actually dim, and maybe 100 neurons in the hidden layer. Actually, let me start off a little bit simpler, and I won't even have any hidden layers. I'll just output directly to the output layer, which will have as many neurons as there are labels. So kind of directly outputting the input to the softmax function here. And so it's kind of going to be exactly like logistic regression, except it's going to have multiple classes. And I should not forget to copy the model over to the GPU as well. So I'll say model equals model.toDevice. And so now let me run this, and I'll just see how it goes, and I'll let you know in a moment. Oh, one more thing I want to show you before the training starts. To keep track of what the accuracy is in the test set, I'm just going to compare the argmax of the labels, which that's the ground truth one hot vector, to the argmax of the softmax output. And so I'm just trying to make sure that the indices of the maximum element in the one hot vector and in the output agree. So I'll just say, you know, num correct equals torch.sum, and so I'll do torch.argmax. So actually it's very much like NumPy again, the API of Torch. So I'll say argmax of labels, axis equals 1. So remember the labels and the outputs are along the rows, it's the different examples, and along the columns it's the dimensions corresponding to the labels. So I'll say, okay, I want the argmax of the labels to equal the argmax of the softmax output. So I'll say outputs axis equals 1. So I'll sum that up, and then that's on the GPU, so I need to get it back to the CPU. So I'll say torch dot, let's see, it should be torch.detach.cpu.toNumPy. I think that'll, or maybe NumPy. I think that'll do it. Okay, so I'll run that through. All right, so the model's finished. Let's look at the results. And what we see is that the loss went pretty steadily down and the accuracy went pretty steadily up. Now, yeah, we kind of topped out at around 90% accuracy. You notice a little bit of wiggling up here. Sometimes what people do is they'll decrease the learning rate as they go on to get it to settle a little bit more into those basins that it's finding. I kept the learning rate kind of small here the whole time, and so that's what we saw. Another thing I want to make to help assess the output is something called a confusion matrix. So I wrote a little bit of code to create this thing here where I'm going to show here the row is a particular type of instrument, and the column is what that instrument was classified as overall the test set. And so this is just what the state that the model finally happened to be in, and I see that, you know, there were more synthetic bass than other instruments, but I'm reporting here what fraction of them they got correct, and you'll see, like, so acoustic guitar was the lowest. There was the most confusion by this matrix. It thought mostly that the acoustic guitars were acoustic guitars, but also thought that some of them were electric keyboards here. You see that a little bit of signal there. And then just another example here, it thought that some of the synthetic basses were also electric keyboards. But overall, it did pretty well in each class, even though the classes aren't totally balanced. So that's cool. Actually, this took a little while. Took about a half an hour on my computer. So let me go ahead and save the model so I don't have to do that again, right? Because there's a lot of data, and I'm doing epics. I'm cycling through, like that 14 hours of audio, whatever, over and over again in each epic. So let me save the model, and there's a way to do this. So I have this tab open here that explains it. I'll throw a link into this, but I have to say torch.save model.parameters. No, it's state_dictionary. Okay. So it's related to the parameters list we saw, and then we give it a name for the file. So I'll call this one shallow.pkl. PKL stands for pickle. That's usually the format that is used. So we can save these parameters so we don't have to train it again. We can load it back and try it again later. But let me try, okay, so I'll also save these images too. But let me try a more complicated neural network, so maybe with some hidden layers. So maybe instead of going directly to this here, I'll go to some hidden layers. Maybe I'll put 100 neurons in the first hidden layer, followed by ReLU. And then I'll put, maybe I'll go from 100 neurons to, I don't know, 200 neurons, another hidden layer. And then finally I'll go from, oh yeah, I need to put a ReLU there, get that nonlinearity in there. And then finally I'll put in a layer from the 200 neurons to the output. And so we can try to train this and see how it goes. So slightly more complicated network. Does it train faster? Does it get a little bit higher than 90%? Let's see. Okay, so we see the performance of this model is extremely good, nearly 100% accuracy. And I don't see a difference between the train and the test set, so I know it's not memorizing stuff from the training set. When I look at the confusion matrix, again, I see almost 100% correct. Barely any confusion. So everything is almost 99% accuracy. So anyway, as people sort of found over the past decade, it does help to have these extra hidden layers. And generally, the more, the better. So that is kind of what we'll see in a lot of the papers that we look at moving forward. All right, so I'm just going to have a couple quick questions for you, and then I'll show you a way that we can tweak something about this a little bit.